In this video lecture, I'm going to go over the concept of NMR spectroscopy. NMR spectroscopy is different from all of the other types of spectroscopy that we've learned about for a few reasons. First of all, it uses the magnetic portion of electromagnetic radiation. Every other type of spectroscopy that we've looked at so far has used the electric part of electromagnetic radiation, and NMR is based on the magnetic component. So if you recall, electromagnetic radiation is two oscillating fields perpendicular to each other. One field is the magnetic component and one is the electronic component. So NMR spectroscopy uses the magnetic component. It works in the radio wave region of the electromagnetic spectrum, and it manipulates the property of spin. So in this explanation of NMR spectroscopy, we're going to be going over the concept of spin and how energy levels are created out of spin and what that kind of means. So we know we need to have some sort of, in all types of spectroscopy, even NMR spectroscopy, we need to have some sort of transition from a ground state to an excited state. And so we're going to look at what that means for NMR spectroscopy and how that's done with spin rather than an electron moving or something else. And then we will also look at the origin of spin-spin coupling. And upfield and downfield shifts and why those occur. So, and finally, the last topic that we'll talk about is sort of how we make an instrument that manipulates or combines all these properties to produce NMR spectra that we're used to seeing. So we're going to start with the, let's see. Okay, so we are going to start with the concept of spin. Spin is the MS. It's the magnetic spin quantum number. And it can have values of either +1/2 or -1/2. And so sometimes we write it as the +1/2 or -1/2, but we also often represent spin as either up or down arrows. Spin is a particularly complex quantum concept for us to understand. We generally simplify it by thinking of the way that the particle is rotating around its own axis, but it's actually more complicated than that. It's a magnetic field vector that particular particle contains. What matters to us is that we know that quantum or spin can interact with magnetic fields. So spin, which all particles, protons, neutrons, and electrons have. So every particle has a spin. Spin can interact with a magnetic field. And there are two types of magnetic fields that are going to play a role in NMR spectroscopy. The first one is an external magnetic field. The external magnetic field is provided by the instrument. It is either a static constant field or a burst or pulse of magnetic radiation. So a static or constant field or a burst or pulse of radiation. So actually NMR spectroscopy uses both of those types of external magnetic fields. The other magnetic field that plays a role in NMR spectroscopy are internal magnetic fields. Internal magnetic fields are magnetic fields that would be coming from within the sample itself. So these would be other spins. And these spins can either be the nuclear spin or the electron spins in the molecules and atoms around it. So one of the main requirements of NMR spectroscopy is that you need to have a net spin. Molecules, or I'm sorry, not molecules, but atoms that don't have a net spin aren't going to be NMR active. So NMR requires a net spin. And NMR, the N we know stands for nuclear. Hopefully we know that. And so what we need is actually a net nuclear spin. EPR is an entirely separate but related field of spectroscopy that deals with electron resonance and electron spin. And so electron spin and nuclear spins have different energies associated with them. The spectroscopies are pretty much the same in general theory, but EPR works in different energy ranges than NMR because it looks at electron spin, whereas NMR focuses on the nuclear spin. So the nucleus contains the protons and neutrons. To have a net nuclear spin, we need to have an odd number of protons and neutrons. So we must have an odd number of protons and neutrons, and that's added up together. Sometimes we call protons and neutrons nucleons, which just means they're particles inside of the nucleus. Some examples of atoms that have a net nuclear spin are hydrogen 1, carbon 13, fluorine 29, or I'm sorry, fluorine 19, silicon 29, phosphorus 31. So different, there's lots of different isotopes, but the isotopes that will be NMR active are the ones that have these odd numbers of protons and neutrons. In addition to needing to have an odd number of protons and neutrons that in order to be NMR active, it also needs to be an isotope that is present in a high enough abundance to be detectable. So the isotope needs to be present in sufficient abundance. If it's an isotope that's makes up a very, very tiny portion of the total isotopes of that element, then it's not going to be very good for NMR because there's not going to be much of it to detect. For that particular reason, hydrogen or proton NMR is probably the most common type of NMR because hydrogen 1 is the predominant isotope. So that makes it very easily detectable, and that's the main type of NMR that most of us are familiar with. You may also have heard of carbon NMR, maybe fluorine, maybe silicon. The other ones become less and less common, but proton NMR is by far the most common. Okay, so we know that we need an odd number of protons or neutrons in the, an odd number total of protons and neutrons in order to be NMR active. If we have that, then we have a nucleus with a net spin. And we're going to call this spin in the nucleus Z, just for a symbol. Okay, so let's say that we put these spins in a magnetic field. Well, first of all, before we put our spin in a nuclear spin, it can point in any direction. So the spin will point anyway in ambient conditions. And so if we have a whole bunch of spins that are not in a magnetic field, they're going to randomly orient. So they'll just sort of point every which way. And as a bulk, as a collection, they cancel out. And so there's no net magnetic field. From the sample. So yes, each individual atom has this sort of spin component, but as a whole, the sample doesn't, because these spins can point in all directions and cancel each other out. However, when we add a magnetic field, so our magnetic field is going to point this way. This giant green arrow will be our magnetic field. And now we're going to put our spins in the magnetic field. The magnetic field we're going to call B naught. That's the external magnetic field that we're applying. And in the magnetic field, spins are going to line up either with or against the magnetic field. When these spins line up either with or against the magnetic field, it turns out there will be a few more that line up with the magnetic field than against the magnetic field. It's slightly lower in energy for it to line up with the field than against the field. So we describe these as two sort of energy states, alpha and beta. And alpha is with the magnetic field, and beta is against that magnetic field. And again, that magnetic field that I'm referring to is the external magnetic field B naught. So it's a little bit more stable for it to line up with the field than against the field. And I did draw a couple more arrows pointing with the field than against the field to sort of illustrate this. So again, this is the higher energy against the field and the lower energy with the field. Before we put it into the magnetic field, when it wasn't in the magnetic field, so in the absence of B naught, the energy is going to be in between these two. All the spins have the same energy because they're not aligned with or against the external field. And then when you put them in the field, they break into these two different groups. And there is going to be an energy difference between alpha and beta. Okay. So whenever there's an energy difference, we can absorb light, and the energy of that light is going to be equal to the difference in the two fields. The case for NMR, however, is that this energy gap is due to a magnetic component instead of the other electronic component. Okay, so there are some equations that go with that difference in energy. The delta E is equal to H over 2 pi, where H is Planck's constant, gamma is the gyromagnetic ratio, which is a unique value that's constant to each nuclei. Whoops, I missed part of this equation. Sorry, there should be a B naught there. So it's gamma H over 2 pi times B naught, where B naught is that external magnetic field. And it has units of megahertz when you put it into this equation. So that's the difference in energy. The energy of the alpha level will be equal to negative gamma H over 4 pi times B naught, and the energy of the beta level will be equal to positive gamma H over 4 pi times B naught. So you can see that the alpha state goes down in energy with the negative sign, and the beta state goes up in energy with the positive sign. We also know from earlier in the semester that E is equal to H nu. So we can sort of combine these two equations, and we get that the frequency of light, the energy difference between these two, is equal to gamma B naught over 2 pi. So that gyromagnetic ratio, which is unique to each nuclei, it depends on what the nuclei is. For the most common values, for hydrogen, the gyromagnetic ratio is equal to 2.68 times 10 to the 8th radians per Tesla second. And for carbon-13, it's equal to 6.73 times 10 to the 7th radians per Tesla second. An additional equation we can look at looks at the distribution of spins between these two energy levels. There is not a huge difference in the distribution of spins, generally speaking. Although I drew a few more in the with the field than against the field. That's how it works out. There's a few more with than against. It's not a drastic difference. So the ratio of these spins nj to n0 or n naught is equal to 1 minus nu h b naught over 2 pi kt. In this equation, what we're essentially looking at here is n naught is the number of spins in alpha, and nj is the number of spins in the beta state. In this equation, K is Boltzmann's constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. T is the temperature in Kelvin, of course, so that our units can cancel out. And then I think we've touched on what everything else here is. So if you use this equation to calculate the relative number of species that should be in alpha versus beta, what you're going to find is typically there's a pretty small difference in distribution between alpha and beta. In fact, you might need like 1,000 spins, and there may be 1,000 spins. There might be like 501 spins in the alpha phase and 499 in the beta phase. So it's not a really big difference in distribution. One of the things that can make the distribution bigger is by making B naught bigger. So if we look at this equation, we don't really have any control or, much control over a lot of these things, but we can increase the strength of the external magnetic field. And increasing that is going to result in a bigger difference in distribution. I'm going to explore this more on the next slide. Lead to... Okay, so if we think about the strength of the external magnetic field, we often draw a diagram that looks something like this, where this would be no external magnetic field, and then maybe like 100, 200, 300. So if you've ever kind of learned anything about NMR spectroscopy before, perhaps you've seen this sort of diagram where you have this difference in external magnetic field. What we're going to see here is as the external magnetic field grows, what also grows is the difference between alpha and beta. And the bigger the difference between the alpha and beta states are, the more likely you are to have spins in alpha than beta. So a bigger delta E makes a more uneven distribution of alpha and beta states. So our NMR at Seton Hill is a 60 megahertz instrument, which in terms of NMR spectroscopies is not a very strong one. Strong NMR spectroscopies, they make ones now that are 500, 600 megahertz. So 60 megahertz isn't that strong, but it still works just fine for a lot of applications. Okay, so I want to explore what this larger distribution does, and a concept of net spin in order to understand the rest of what happens in an NMR spectroscopy. So we know that in this magnetic field, the spins are going to either line up with the field or against the field. And as this happens, as these spins line up, let's get our field in there again. So again, the big green line is going to represent our external magnetic field B naught. As these line up with and against the magnetic field, we're also going to form a internal magnetic field, which I'm going to call M sub Z. M sub Z. So this is going to be the net magnetic field of our sample. So any of these arrows that are pointing up and down are going to sort of cancel each other out. So let's see, these would cancel, these would cancel, these would cancel, but we're going to have a couple spins left that don't have anything to cancel out with. These are going to be what makes up our MZ. That kind of looks like a 2 instead of a Z. That should be a Z, named after the Z axis. Just sort of arbitrary. So the greater the difference in delta E up here, the more spins there's going to be in alpha versus beta. And that's going to, oops, I'm sorry about that. That's going to lead to a stronger M sub Z. So this M sub Z is actually what is monitored and detected in an NMR spectroscopy experiment. So the stronger we can make M sub Z, the more efficient the analysis is and the better the method works. Even for proton NMR, where it is the H1 is the main isotope, so you would have it present in higher concentration, because of the fact that there's not a huge difference between the alpha and beta states, and we're not dealing with a very big energy difference. NMR is not a sensitive technique. increasing the external magnetic field can make it more sensitive, but even in like a 500 megahertz instrument, it's still going to have limited sensitivity, and it's not going to be very good for dilute or tiny samples. So you need to make sure you have a decent amount of sample in your NMR tube, and it can't be a really dilute sample, because then you're simply not going to have enough to detect, because you're relying on a very subtle difference in the population of spins between alpha and beta to create this detectable M sub Z magnetic field. Okay, I'm going to stop this video here just so the file doesn't get too big and too long, and then start up in a second NMR spectroscopy module to talk about what happens once we've established that M sub Z and how we do an NMR experiment.